you may need to put some effort and write some things to show that the mapping is well defined. And keep in mind that whenever a mapping is given to us, we have to make sure before we do something with that mapping that the mapping is well defined. If it is not well defined, it's not even a mapping, and then we cannot work with it in the usual way we work with mappings. Okay, so this was the third example. Now we come to example 4. Let j be the, we already know j is the set of integers. What is the need for writing it? Let j be the set of integers and let S be the set of ordered pairs of integers such that the second coordinates are non-zero. Okay. Define tau from j into, okay, not from j into s, but define tau from, I should have written that t. Before defining it, I need the set of rational numbers also. Let t be the set of all rational numbers. Define tau from s to t by this. Unlike the previous example, here there is no problem verifying that tau is well defined. So what we are doing is we are taking ordered pairs from S and we are applying tau on that ordered pair where the components or the coordinates are integers and the second coordinate is non-zero. So we can form this ratio and it is going to be a rational number. And note that since an ordered pair like this has only one representation, this m comma n is not equal to some m prime comma n prime unless m is equal to m prime and n is equal to n prime. So for this ordered pair, m and n are unique, and as a result m by n is also unique. So that means our function is well defined. So this is another function or mapping. Then example 5. Let S is equal to j cross j. The Herstein writes j is the set of integers. It's how many times he is going to write this, I don't know. We already know that. Define tau from S to j by this. That is, here what we are doing, we are just taking a pair of integers and we are adding them. Their sum is the image. Now here there is a remark. Note that in example 1 to 5, the addition in J, that is ordinary addition of integers, can itself be considered as a mapping from J cross J to J. So what we are saying here is that the operation addition itself can be thought of as a mapping, where the first set is J cross J. We take two integers and the second set is J. That the mapping gives us their sum. Using this idea, we can define the concept of a binary operation. Given a set S, any mapping from S cross S to S is called a binary operation on S. Binary because there are two S's involved, and as such there will be two elements involved in the operation. If there are three elements, then the operation will be called ternary operation. So there are arity of operations. Okay, an ordinary function is called unary. Okay, the n-ary operations are also there, where n can take any positive integer value. We can use this to define a product on S. The word product is within quotes because it's not actual product. I mean ordinary product or multiplication. It is a product that is just an operation between two elements. If tau from S cross S to S, okay, the product can be denoted by a symbol star, say. If this is a binary operation, then for A, B and C, for three elements in S, by C is equal to A star B, we mean C is equal to the image of A comma B under tau. Okay, so that's how we can define a product. In fact, that's what we have done here. Here the addition on integers, that is the binary operation tau, and we have used it to define a product which is actually the operation addition. The symbol star here plays the same role as the addition symbol here. Okay, here we are dealing with integers and ordinary addition. here we have an arbitrary set and an arbitrary operation, arbitrary binary operation. Okay, so next we come to the sixth example. Let S and T be any sets. Keep in mind they have to be non-empty according to us. Define a function from S cross T to S by mapping the ordered pair S comma T onto the first coordinate S. Okay, so in this case the ordered pair is mapped onto its first coordinate. So clearly for this given ordered pair, the first coordinate is a unique element in S, so the mapping is well defined. This mapping tau is called the projection of S cross T on S. Similarly, projections are important mappings. Okay, you will encounter this in several places in mathematics. Instead of taking two sets, we can take any number of sets. Similarly, we can define the projection of S cross T on T. To understand why such a mapping is called a projection, you take in place of S and T, let us take the set of real numbers. So if we have this mapping, where this is mapped onto S, then we can at least try to understand the situation using coordinate geometry or using the association of R cross R with the plane of geometry. So if we have our point S comma T, then it is a point in the two-dimensional plane. Now what this mapping does is that it maps this point onto the first coordinate S. So it can be thought of as a projection of the point onto the first axis, x-axis. If you define another map which maps this ordered pair onto the second coordinate, then it will be like this. It will map the point onto the second axis. These are called projections because we are projecting the point onto the axis, or these can be treated as shadows of the point. If someone is shining a flashlight from above and the point is here, the shadow will lie here, right? The flashlight is perpendicularly downwards, or if someone is pointing a flashlight from this side horizontally, then the shadow of this point will lie on the axis here. So these shadows are the projections, they are being projected onto the axis. So that's why such mappings are called projections. This of course is a situation where we can use diagrams, but in general we cannot think of such things. Projections are important in topology also. Okay, then we come to example 7. In this example, we are just going to take a set with 3 elements and define some particular map. Let S be the set consisting of these 3 elements x1, x2 and x3. Define a map tau from S to itself by defining the image of x1 to be x2, the image of x2 to be x3 and the image of x3 to be x1. This is also a legitimate mapping. Every element in S has a unique image, so it's a well-defined mapping. Then we have example 8. Let S be the set of integers and T be the set consisting of the words O and E. Define a mapping tau from S to T by this formula. Any integer n is mapped onto the letter E if n is even and is mapped onto the letter O if n is odd. This mapping is well defined because every integer is either even or odd and not both at the same time. Okay, that's why this mapping is well defined. Right. Okay, so next comes those things. Let S be any set. Let x1, x2, etc. up to xn be the subset of S consisting of the elements in S. That is, if you have a non-empty set, you can consider several subsets of that set. That's what I think the author tries to say here. In particular, we can consider the subset X of S consisting of the single element X belonging to S. We can consider, or we can take all such subsets of S and create a set S prime, I mean S star, known as the set of subsets of S. That is, S star is nothing but the power set of S that you already that we normally know as. The relation of S to S star is in general an interesting one. We shall explore this relation in some exercises. And we now use this idea of the power set of a set to give our next example, the 9th example. Let S be a set define a function from S to S star. So here the first set is S, the second set is the power set of S, or in other words the set of subsets of S. By mapping an element onto this set. That is, we are taking an element from S and we are mapping it onto the complement of this set consisting of the single element S. And note that since this is a subset of S, this is an element in S star, and for a given S, this set is unique. So this mapping is well defined. And lastly, we present one example that involves equivalence classes. Let S be a set on which there is an equivalence relation. So if there is an equivalence relation on S, then according to theorem 111, you already know that there will be equivalence classes which will whose union will be equal to S and the classes are mutually disjoint. Those things are there. Let T be the set of all the equivalence classes in S. Keep in mind that the equivalence classes in S are after all subsets of S. That's why note that T is a subset of the power set of S. Define a mapping tau from S to T by mapping an element onto the equivalence class containing that element. For a given element, whatever it may be in S, there is an equivalence class corresponding to it, and there is only one equivalence class which contains the given element, because distinct equivalence classes are disjoint. That's why for a given S, this class of S is unique. So this tau is well defined. Right. Okay, now we leave the examples and discuss some general things. Given a mapping tau from S to T and an element T belonging to T, we call the following set the inverse image of T under tau. This set is called the inverse image of T under tau. So we are given a mapping and we have chosen an element in the second set. So the inverse image of this element under the mapping is actually the set of those elements in the first set whose images are equal to T. So that is the inverse image of T under tau is the set of those elements in S which have T as their image under tau. Okay. Note that for a given t belonging to T, the inverse image of T under tau may be empty. That is, T may not be the image of any element in S under tau. This may happen. In fact, we can give example, but let me first put, I think I am running out of ink. In the third example that we have seen, such a situation occurs. In example 1, 2, 3, the inverse image of this ordered pair under the mapping used is empty. If you remember, it is that mapping which takes a positive rational number, then gives you the ordered pair of those integers, positive integers, whose ratio is equal to that positive rational number and which are relatively prime. So since these 4 and 2 are not relatively prime, so this pair will not appear as the image of any rational number, any positive rational number under that function tau. So the inverse image of this under tau is empty. Another such example is here, this one. In example 1 to 9, the inverse image of S in S star is empty. Now, because S is also a subset of S, so it is an element in S star, but if you want to find the inverse image of this under that function tau, then that will be empty. Why? Because you see, the images that we get under this mapping are all proper subsets of S, because one element is being removed from S. So no such image can be equal to S naturally. So that's why the inverse image of S remains empty. Okay. Now next we come to the very important concepts of one-to-one and onto mappings, or which are otherwise also called surjective and injective mappings respectively. This classification is very important, and the most important class of mappings are the ones which are both one-to-one and onto, or in other words, the bijective mappings. Anyway, we go with the definitions. a mapping tau from S to T is called onto if for every t belonging to T there exists S belonging to S such that T is equal to S tau. So it is exactly what these situations are not. Here you see, here S does not has an empty inverse image. Here 4,2 has an empty inverse image. If our mapping is onto, no element in the second set will have empty inverse image. That's the thing. Every element in the second set will be the image of at least one element in the first set. That's what we have written here. For every t in T, there will be some element in the first set whose image is T. If we call the set S tau, which is defined like this, T belonging to T such that T is equal to S tau for some S